Okay, so I didn't understand what Leonardo said because I don't speak Spanish. So sorry for my crappy accent. I'm French. We are not used to speak really well in English. So sorry, translators. It will be that way. So I work at the ADS, and at the ADS we built a new project which is called SECCOMP that I will present to you today. So what is SECCOMP SECCOMP is basically just a sandboxing environment on Linux. So this is focusing on headless applications. So it is not designed to build a sandbox on a full GUI application like Firefox or whatever. So it's just designed to run headless applications like cloud applications. One of its particularity is to not require any recompilation. You don't have to have the source of the application that you want to sandbox. You just have to run it like this. No recompilation, no instruction rewriting, nothing at all. Furthermore, there is no kernel patch which is needed, because when you have to integrate some patches to the kernel, it's really hard to get it right. And when you make some modifications, you have to maintain your patch all over the time. So it's really time consuming, and the kernel maintainers are really don't want to have this kind of thing into the kernel. So we had to work only on user space. And the best feature of SECCOMP is that it is a free software, so you can already download it on my webpage, and you can run it right now. So why another one sandboxing environment? This is because today there are some solutions like the one based on chroot plus capabilities. So basically this is just using some kernel infrastructure to limit the ability of a process to not do anything he wants. But the main problem of this approach is that there is a huge attack surface available to an attacker who would compromise a process. So if you run an application into this kind of sandbox and this application gets compromised at some point, then it would be easy for an attacker to bypass the kernel protection and to evade from this kind of jail. Like it's really easy to evade from chroot jail, because without patches like GR security, you just have to mess up with the /proc entries and you're done. You could really easily go out. So this is not the best solution available for sandboxing. So there are some, which is the most popular option is to use ptrace. Ptrace is just an infrastructure on Unix to debug processes. So basically, at the beginning, when ptrace was developed, it was only used for debugging reasons. It was never written in order to do some security stuff. So it's really hard to use ptrace correctly. Because of that, and because of the complexity of ptrace, there is a huge attack surface too, because the kernel has to maintain a lot of things, a lot of states. So it's really hard to get it right. And when you are tracing a process, so you're the tracer and you want to sandbox an application, so you have to trace it, and you have to verify that each action that the process will make is allowed or not. But the problem is that making the decision is really hard. To validate a system call, it's really hard to make it right, because there are some race conditions, there are some means interpretation between the kernel and yourself, so you will not interpret the data the right way. And there is also problems of synchronization. Every time you think about threads, it will be a nightmare to really correctly validate the syscall. It's also slow, because each time a process will make a system call, there will be a round trip between the kernel, then with the tracer, then the kernel, then the tracee. So it's really slow. So it's not the right solution. The most recent sandbox methods are based on role-based access control, which is based on Linux or on the Linux security modules. The most popular example of this kind of sandbox is the XGuest package of Fedora. The Red Hat people wrote this sandbox, which is only using Linux in order to sandbox an application. The problem is that the Linux security modules are a nightmare to secure. So there is a huge attack surface too, and it's really easy to exploit the bug into the kernel, and when you exploit the kernel, you're done. There is nothing to prevent an attacker to evade from your jail. So Brad Spengler, the author of Giraffe Security, is very vocal people against Linux. So he wrote a lot of exploits to just prove the point that Linux is not designed for security, even if the name of Linux is Secure Linux. But some people prefer to use virtualization, either by using hardware virtualization or software virtualization. So this is the approach of Cubes OS, the project of Invisible Thing, Joanna Ostovka. We designed Cubes OS, and in fact, it was estimated that it was just a shift of the attack surface. So before their project, the attack surface was the kernel, but now the attack surface is in the hypervisor. So you just shift the attack surface, and that's all. You are not most secure. This is just that today attackers are not really don't have common exploit on hypervisor, but it's just a matter of time. So all these sandboxes have some kind of problems, but the common problem of all these solutions is that they all offer a huge attack surface for an attacker. A sandbox is designed to run untrusted applications, so you want to be able to run whatever you want. You don't have to say, this file comes from something, do I trust it? No, you just want to run it and see if it works. So Google Chrome has the same problem with their browser. So they wrote a sandbox, a very specialized one, which is based on SECCOMP. So I will introduce SECCOMP. So SECCOMP means secure computing. This is a very Linux-specific feature, which is neither designed in POSIX or single Unix specifications, or even in BSD. This is really, really Linux only. It was introduced in 2005 in the 2633 kernel, so this is a bit old, but it was never really used. It was designed by and implemented by Andrea Arpenengi. So just for the story, Andrea is the founder of a company called CPUshare.net. This website at that time in 2005 was providing some service. You had to send him some jobs, and he would run into on this platform. This was the very basics of the cloud computing, when at that time we didn't call it cloud. So Andrea had the problem of he needed to run applications from nobody, from everybody. So he couldn't trust it. So he wrote this feature. So this feature, what is it? So when you're a process and you want to use SECCOMP, you have to go, you have to enter into it voluntarily. You can't say, okay, I'm this process and I want this process to enter into SECCOMP. No, that's not working like that. You must issue yourself, okay, I want to enter into SECCOMP. That's all. When you enter into SECCOMP, your process is only allowed to do 4 system calls. These system calls are read, write, seek, return, and exit. Underscore exit, which is important. If you do any other system call which is not allowed, then the kernel will send you a seek kill. And the seek kill signal is not maskable, not ignorable, or whatever. So you will be killed, that's for sure. So it could be an interesting method to sandbox a process, because this is very safe. Because if my sandboxing system is not working properly and there is a bug, then the application could try to issue a new system call But because the kernel is really picky, and if you are really trying to do a system call which is not allowed, then we saw that the kernel would kill you. So there is no problem, this is very safe. So even because I'm not really smart, so I prefer to have this kind of limit. I know that if I mess up, okay, the kernel will take care of the process, so no problem. Then the most interesting feature of SECCOMP is that there is a very, very little attack surface. The kernel attack surface is really limited. For example, we reviewed the 440 vulnerabilities which were published on secunia.com, and we reviewed each of them. And we saw that only 13 vulnerabilities were triggerable from a SECCOMP process. So that's really a tiny fraction of the vulnerabilities. And the 13 vulnerabilities were just simple denial of services or that kind of thing. It was not remote code execution or this kind of problem. So you could think it's really safe to use SECCOMP. When a process is in SECCOMP, it could be safe. But the problem is, if you want more details about these 13 vulnerabilities, I do some publicity for myself, you can follow this link. So we thought that SECCOMP was the perfect tool to make a sandbox, so we designed SECCOMP Nurse, which is our project. But the problem of SECCOMP is that it is so limited, the attack surface is so limited that you can't do anything. If you read this really simple program, which is basically just an hello world, then, so here the first instruction, I'm doing a PRTTL call, which is the call to enter into SECCOMP. So this program enters into SECCOMP, and then it writes on stdout the string hello Ekoparty. So we could think that it's okay, it's a really simple program, so it should run fine under SECCOMP. But the problem is that the return 0 statement is translated by the compiler into the exit system call. And we saw that the fourth system call was underscore exit and not exit. So the program gets killed when it arrives here. So we can see that the kernel and SECCOMP is really picky. You have to be very careful about how you use it. So there are two problematics by using SECCOMP as a sandbox. The first one is how to enter into SECCOMP. Because we saw that entering into SECCOMP is a voluntary process. So we want to run applications which were not designed to be run into a sandbox. So we must find a way to enter into SECCOMP for this kind of process. So this is our first problematic. And the second one would be, okay, this application is doing something. So we have to manage it to run. But we saw that we have only 4 system calls which are allowed. So how to do that? How to prevent the applications to not make forbidden system calls. So this will be our second problematic. So let's start with the first one. So entering to SECCOMP. We had some constraints when we were thinking about this problem. The first one was that we don't want to use ptrace, because ptrace is hard to get it right, is really a null system call which is complex to use it safely, so we don't want it. And this is a very popular solution, so we try to innovate sometimes, so we try to find another solution. Still, we have the constraint of no recompilation. We don't want to have any modification of the source code or the modification of the binary file. So we don't want to do any instruction rewriting on the fly. So the first solution that we think was to use preload, the preload feature of the GNU linker. So the GNU linker has a feature of you can overload any symbol of a library. When you look at how applications run, you can see that the libc start main is the first function which is called by the linker, and this function is available into the libc, and the libc is then calling the main function of your application. So we thought that it was a good idea to just overload this function, and then we would enter it to SECCOMP, and we would call the real main function. But, okay, it works. But it's really not funny, because everybody knows about that. So we thought for another method, which is a very not popular one. This is a GNU linker feature, which is called audit library. So this feature is just documented into a main page, and this main page just says that it provides an auditing API that allows an application to be notified when various dynamic linking events occur. So basically, that means that every time the linker would have an action, then there will be a set of hooks, and these hooks will permit you to be notified. So each time the process is doing a DL open or DL theme function, then our hooks will be notified. One particularly interesting hook is at the initialization time, when the process is going to be run. So just before the main function is run, you have a hook. So in this hook, we just allocate some pages for our code and some of our variables. Then we intercept syscalls, because we will have to do that later. And then we enter into SECCOMP. At this point, we just have to run the main function of the interested application, and that's all. So from now on, the application would run into our sandbox. To use it, so you just create this audit library, and you have to call the linker explicitly with this kind of command line. So I'm running the ls command with the sandbox.so audit library, and that's all. But the problem of this approach is that this feature is barely used. There is there is only one project which is using it, which is called Latrace. Latrace is an equivalent of ltrace, but the ltrace original program is using ptrace, and Latrace is only using the audit library API. So there is only one application on the internet which uses this feature, and when you have a bug, it's really hard to find out what's going on, because the upstream maintainer of the audit library is Ulrich Rapper, which is a not really friendly guy, and he doesn't really like when you report bugs. So when you report a bug to him, you have to be really sure that it is not you that he's doing a wrong thing, because he's really not cooperative. The problem of the audit library API is that it's barely documented. There is only one man page, and that's all. So you have to work with that. So currently we have a problem with the thread local storage space, which is not behaving normally, because we are just running before the main function. So not everything is set up when we are called. And it seems that the thread local storage is not in the right condition. So we have a bug, but for the moment it's it's sufficient for use. So now we found a way to enter into SECCOMP for a process, for an application, but we still have our second problem, which is we have to prevent applications from doing forbidden system calls. We have the same constraints like usual. We don't want to use ptrace because it sucks. We don't want to do the library overloading stuff, because we could say, okay, if the process wants to open a file, it will use the open function available in the libc. We just have to overload the open function. Okay, it would work, but the problem is that you would have to overload the open function, fopen, freeopen, fdopen, and blah 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 and blah blah blah. So there will be a lot of functions. You would have to have like 1,000 functions to overload. So this is not possible. We still have the problem of the constraint of no recompilation issue. We don't want to have any modifications to the source code or whatever. So we looked at how system calls are made on a modern system. Here is on the left side a dump of the kill function available in the libc. So we can see that it is moving around arguments. Then it puts the 0x25 value into EAX, which is the system call number of kill, and then it does a call GS 0x10. So we can see that on this kind of platform, so on the modern x86 platform, the libc is no longer inlining interruptions. Before, to make a system call, you just had to do an interruption like int 0x80. So now, instead, you have to call an indirect function which is stored in the VGSO. VGSO is a page which is published by the kernel because of the evolution of the CPUs. A long time ago, it was really fast to do interruption. But with the availability of the Pentium 4, we saw that interruptions were really slow. So we found a new way to make system calls with a dedicated set of instructions called sysenter and syscall. But the problem is that the libc, when you are, if you are using the libc package of your distribution, of your Linux distribution, this package has to be run on old system and modern system. So it would be really not efficient to inline here either the interruption stuff or to do the sysenter instruction. So the best way was, at boot time, when the kernel boots, it will find what is the most, the fastest way to make a syscall, and it will save this, the best method somewhere. So when user space wants to do a system call, it just has to jump into this VGSO page, and that's all. The libc will always use the fastest way of making system calls. So if you have, for example, a Ubuntu system or Debian system, and you already ask yourself, what is this package called libc6-686, and what is it? What is the difference between this package and the classic libc6 In fact, that's just that with the classic libc6 package, instead of this call function, call instruction, you have the interruption. So this is only the only modification of this package. So this is interesting because we can see that this instruction is an indirect one. So you have to call an indirect function, and it's possible to overwrite the GS register. The GS register now points into a zone which is controlled by ourselves, and it points into our handler. So now, when a system call is made by the libc, it will automatically intercepted by our handler. So this is only right for legit system calls. If the application is trying to do some inlining, so it tries to inline assembly, like making direct interruption in the REXAT, then we will not intercept it. The handler will not get it. But we saw that SECCOMP was fail-safe, so the kernel will prevent the application from doing this kind of thing and will kill the application, so there is no problem. So if the application wants to do some weird system call, okay, go on, but you will be killed, no problem. But the problem is, okay, we managed to intercept system calls, and now what can we do? Because the handler, which is intercepting the system calls, is still running under SECCOMP, so we can't do anything else. So we have to introduce another process. So when your application is running, in fact, we have another process which is running in parallel. And this other process is called the helper. So now, when the untrusted application makes a syscall, this is intercepted by our handler, and the handler will notify the helper thanks to a Unix socket. Then the helper will receive the request, will do something or not. So we will check if the process is allowed to do this. We have our own security policy engine. So if this is allowed, we do something. If this is denied, then we say, no, I will not do that. That's all. So we are at this step now. So the helper will pass a return value to the ender. So if this is an error or the true return value of the system code, and then the ender will just give the return value to the untrusted application. So from the untrusted application point of view, it was transparent. He doesn't know if there is a sandbox involved or not. But in fact, it's a little bit more complex. So we have our two processes. On the right side, you have the helper, which is an application that we wrote. And on the left side, you have the untrusted process. And the untrusted process is composed of two threads. The thread on the right, the green one, is the trusty, what I call the trusty. So this is the trusted thread, which is running trusted code. On the left box, the red one, you have the untrusted, which is running under SECCOMP, and this is where the original program, so the untrusted application, is running. So when a syscall is made in the untrusted, our handler kicks in and notifies the helper. The helper, so this process, is written in Python. It implements some kind of access control, so there is a whole policy engine inside it. And so the helper will take the decision if the syscall is allowed or not, and if the syscall is allowed, then it will delegate the syscall execution to the trustee. So the trustee now is a tiny assembly routine, which is just about 200 lines of code, which is just listening for orders from the helper. So this tiny assembly routine is just executing orders. That's all. And you must ask yourself how it could work. So this is because of thread voodoo. So if we took a quick glance of Programming 101, we know that threads share everything. They share address space, so all the memory is shared between the two threads, but even the file descriptors and logs are shared. So if you open a file in a thread, it will be available in the other. So in other words, that means that any action is propagated between threads. So this is really interesting, because that means that if the trustee makes an action, it will be available for the untrustee. So from now on, we'll be able to perform syscalls on behalf of the untrustee. So that's cool, but it's really dangerous, because the trustee, the tiny assembly routine, is running into a very hostile environment. So the trustee has to be written very carefully in order to never use shared things like memory. So the only thing which is not shared between two threads are CPU registers. So our assembly routine is just using CPU registers, that's all. So this is really hard to make it work, but it works. For the helper now, so there is some kind of policy engine. So when a syscall is intercepted, this is not sent to the helper, and the helper has to decide if the syscall has to be really made or not. So basically, here is the actual code of the policy engine of SECCOMP, which is composed of the open syscall and the access security check. So if we take this security check, so when the untrusted application is trying to open a file, this security check is asked. If this function returns true, then okay, the system call will be made by the trustee. Otherwise, if the system call is denied, then return false, and the untrusted application will get an error. So this really simple check is just checking that the file name which is requested is inside the whitelist. So we have a very simple whitelist, and we just check if the sandbox can open this file. That's all. So you can see that it's really simple to write the policy engine. But for the access one, I was too lazy because I didn't want to implement it. So for the moment, it's just implementing, it's just returning true all the time. So it's not really safe, okay? But it was just for the proof of concept. So now it's time for the demo. I hope it will work. But if it don't work, I have a video fallback, and if the video fallback does not work, I have a cheat sheet somewhere. So, I hope that you all see. So this is a real classic system. So this is the upstream kernel of Debian with the 686 platform. So this is not the one that is installed by default. You can see that I'm not administrator, I'm not root, so I'm just a classic user. So I compile the stuff, which is really fast. You can see that there is a secret file where I just say I love my mama. So it exists. So now I just want to sandbox the Python interpreter. So I just have to write it like this. So it is. So the Python interpreter is waiting for instructions. We can see that there are some errors. So it's just saying that these syscalls are not implemented for the moment. But when my SECCOMP see a system call which is not implemented yet, then it just fake to the interested application that it works. So sometimes it makes the program crash, but it works most of the time. So I can write some classic Python code, there is no problem. It works. I can open file. Okay, no problem. It works in the sandbox. I can import modules, like usual. Oops. So this syscall is not yet implemented, so it returns 0 by default. So now maybe you ask yourself, if I do the open like that, will it work within the security check? So let's try to open the secret password file, which is not in the whitelist of the policy engine. So no, I get an error. So the kernel said there was an operation not permitted. So the sandbox is working properly. But you saw that the open syscall security check was correct, but the access one was empty. It is always returning true. So now, if I try to access this file, I get true. So the system call was really made, the access system call was really made, and it returns true. So here it is for the demo. So what is the status of the project? So for the moment, the core system is implemented. So we have all the foundation of the project to do it. We also finished, and we can trust SECCOMP because the trust is self-protection, because I said that the trustee runs into a very hostile environment, so we must be sure that we work properly. So we think that this is correct, but what is not implemented, for the moment, this is most of the security engine. We have to write a lot of security checks like we saw before, so this is not really complex. This is just a matter of time, and we don't have really much of time. So this is just classic Python code that needs to be written. So is it usable now? Yeah. Every tool that I want to run runs on SECCOMP. So every time you see a headless application, you could think using a SECCOMP, like using it for image manipulation. So imagine that your iPhone is now using this kind of thing, then you could not jailbreaking it anymore. So maybe Apple will want to do this kind of thing later. You can also want to use some PDF transformation, like PDF to text. Imagine that on your mail server, you want to automatically decode PDF file, transform it into ASCII, and write it into the mail safely. Then you could use SECCOMP in order to open every interested PDF file and transform it. So that works. There is no problem to use PDF to text, for example. You saw that we can run the Python interpreter. So if you want to implement a new Google App Engine, you could use this kind of thing. So that works. So now for the limitations, there are some. Like this is a Linux-specific tool. It will be never available on BSD or whatever you want, just on Linux. You also need a recent GNU Linux. By recent, this is just a 2005, so it's okay. You just have to compile it for 686 platform and not the 386. And there are some syscalls that will be never implemented, like everything which is really related to the clone system call. So every time you try to do, you try to create a thread or a process, then we could not support it. We could, I think, but it would be insane to support it. So I prefer to let SECCOMP to be really simple, because otherwise it's really easy to make it wrong. Then the other syscall which will be never supported, that for sure, this is execv, because it's impossible to make it. There is still a problem with the function GLOpen, because GLOpen in the Linux is not using the classic call GS10, but it is the only function which is inlining the interruption. So because this is inline, I can't intercept it, so I can't use it. In the future, so I just want to implement more syscalls. I could use also some bits of the Google Chrome project. They designed a standalone library recently, so we could use it instead of my tiny assembly routine, because I suck at assembly, so maybe it would be better to use it. And I hope to get some peer reviews, because it's really easy to make it in myself at work, but I want the maximum of people to review the code in order to use it widely. So no problem, it's me. You can find every bug you want. I don't have money to give you if you find a bug, but I promise that if you find a security bug, or even a bug, I will send you a postcard of the Eiffel Tower, or some poopies if you want. Sorry, I don't have money. So thank you for your attention. If you want to download the software, this is available at this URL, so be my guest.